In the last lecture, we completed up to number 4 on worksheet 16. So in this lecture, we'll continue worksheet 16. We'll do the last problem, which is number 5, and then we'll move on to another worksheet. So on number 5, we have a uniform horizontal beam with a length of 8 meters and weight of 5200 newtons. We'll make it 200 newtons, okay, instead of 5200 newtons. Please cross that out and then write 200 newtons. So it is attached to a wall by a pin connector. Its far end is supported by a cable that makes an angle of 53 degrees. So this angle is 53 degrees with the beam as shown in the figure. A person of weight 600 Newton stands at a distance 2 meters from this pin connector. Find the tension in the cable as well as the magnitude and direction of the force exerted by the wall on the beam. So the first thing we need to do to solve this problem is to draw the extended free body diagram. So meaning we want to write down all the forces that are acting on this beam. Okay, so the first force is the tension due to the rope. The next one is, we assume that the weight of this beam is concentrated at the center, which is halfway its length. So that's the weight of the beam. And then this person is standing at 2 meters from the wall, so this person also exerts force on the beam with its weight, so WP. And there is force of this pin connector on the wall on this beam. Let's call that vertical force. And we know that this force exists because in absence of the pin connector, or in absence of this force, this beam would just slide down through the wall. Okay, so again, because of this force, the beam remains at its position. And then also there is normal force of the beam on the normal force of the wall on the beam, and because of which the beam doesn't move to the left. Okay, so let's call this force F, F horizontal, FH. Okay, so these are the forces that are acting on the beam. So then next thing is, we want to use the condition for static equilibrium, because the beam is in static equilibrium. So the conditions for the static equilibrium of the beam are the sum of all the forces along x direction is 0, sum of all the forces in the y direction is 0, and sum of all the torques is 0. Okay, so let's apply this first condition. We want to add all the forces along x direction. So for that, we need to know what forces are acting along x direction. One is this one, so this is acting along x direction. And the next one is, this tension has two components. One is this horizontal component, and the next one is this vertical component. So this is phi, so that means this would be t cosine phi, and this component would be t sine phi. And if we consider this right side to be positive x and up to be positive y, then this would be negative t cosine phi. Okay, so that's the x component of the tension, and we have this force along the x direction, which is positive. It's pointing to the right, so that is equal to 0. Now let's add all the forces that are acting on y-axis or y direction. So the first one is Fv. Fv is positive because it's pointing up. Wp is pointing down, so it's negative. Wb is also negative because it's pointing down, and then y component of the tension is pointing up, so it's positive. Okay, that is equal to 0. And the next one is to find the net torque or sum of all the torques. Now to find the torque, we need to first define a pivot, and again, like last time we discussed about how to determine a pivot. To determine the pivot, we look at the unknown variables. Okay, we will choose the point as a pivot where there are one or more unknown variables. Okay, this point, we could choose this point as a pivot, but there is only one unknown variable here. But here we have two unknown variables, Fv and Fh. So if we choose this one, then we won't have to deal with the two unknown variables. Okay, so that's why we will choose this pin connector as the pivot. So choose the pin connector as the pivot. Okay, then we will find torque for each of the forces. So for tension, the distance, by the way, the torque is given by Rf sine phi, where phi or theta, this angle, is the angle between R and F. So for tension, distance between the tension and the pivot is the length of the rod or the beam, so L, and then force is T, sine angle between the R distance and force is phi in this case. And this tension, if you consider this to be the pivot, when you pull this beam in this direction, it tends to rotate the beam in counterclockwise direction, so that means this would be positive. Now the next force is Wb. So Wb tends to rotate this beam in clockwise direction this way, so that would be minus. Then distance is halfway through the length, so that means L over 2. Force is Wb, and the angle between the distance, this distance, and the force is 90 degrees. Okay, that's 90 degrees. Likewise, Wp also tends to produce clockwise rotation, so that's negative. Distance between Wp and the pivot is 2 meters, and force is Wp, and also angle between the force, which is down, and this distance is 90 degrees, sine 90 degrees. And then Fv and Fh do not produce any torque because distance between the forces and the pivot is 0 in this case. So R is 0, that means T is 0 or tau is 0. So that is equal to 0. So now we need to decide which equation of the three, 1, 2 and 3 would be useful to find the unknown quantities. So first thing we want to find is tension. So in this equation we have T unknown, FH unknown, so there are two unknowns, that means we cannot use that. Here also we have this unknown and this unknown, so we cannot use that. But on the third one we have all the quantities known except T. Okay, L is known, phi is known, WB is known, WP is known. Okay, so everything is known. So let's use 3 to find tension. So to find T, so plug in the numbers. L is 8 meters, T is unknown, sine phi is 53 degrees, L is 8 meters over 2. WB, weight of the beam, is, we are considering that to be 200 newtons. Sine 90 is 1, 2 meter. Weight of the person is 600 newton, and sine 90 is 1 again, so that is equal to 0. So we want to move these numbers on one side and then the one with the variable on the other side. So keep this as it is on the left side. So 8 meters sine 53 degrees times T. Okay, and then move these things to the right. So this and this cancel with 4 remaining. So if I move this to the right, this negative becomes positive. So 4 times 2 is 200 is 800 Newton, and then meter, minus 2 times 600 is 1200. By the way, this negative becomes positive when it moves to the right. So 1200 Newton meter. Okay, so now to find T, we'll divide both sides by this quantity, this term. So T is equal to 800 plus 1200 is 2000 Newton meter over 8 meter times sine 53 degrees. Okay, so when you do the calculation, what you get 313 Newton. Okay, so tension is 313 Newton. Now the next thing is we want to find the force of the wall on the beam. So there are two forces due to the wall on the beam. One is this vertical force and the other one is this horizontal force. So we want to find the combined or the combination of these two forces, because these are the individual forces, so we want to find the combined effect. So to find that, first we need to find the individual VH and FH and FV. So to find that, we can use either equation 1 or equation 2, or we need to use equation 1 and 2. So let's use equation 1. So by using equation 1, we can find FH, because T is now known and phi is also known. So use 1 to find FH. So we can move this term to the right, so that will give us FH is equal to T cosine phi. T is 313 Newton and phi is 53, so cosine 53 degrees. So let's look at the calculation. 313 times cosine 53 degrees, that is 188.38, 188 point, let's say 4 Newton. Now let's find FV. So to find FV, we will use equation 2. So use equation 2 to find FV. So this is what we want to find. So leave this on the right side and take everything to the leave this to the left side and take everything to the right side. So FV is equal to WP plus WB minus T sine phi. So WP is the weight of the person, which is 600 Newton. WB is weight of the beam, which is, we are considering that to be 200 Newton, minus T is 313 Newton sine 53 degrees. Okay, 600 plus 200 is 800 plus minus 313 sine 53 degrees. So let's see what that is. So 800 minus 313 sine 53, so that gives me 550 Newton. Okay, so we found FV and FH. So FV is pointing up, FH is pointing to the right, so the resultant of these two would be somewhere in between, and that is given by the Pythagoras equation, which is F is equal to x component square, which is FH squared, plus y component square, Fy or FV squared. So FH is 188.4 squared and FV is 550 squared. So let's see what we get. So square root (188.4 squared plus 550 squared). So that gives me 581.37, 581.4 Newton. Okay, so the force of the wall, or the total force of the wall on the beam, is 581.4 Newton. And we also need to find the direction, okay, which way the force is, the net force is exerted on the beam. Okay, so the net force would be somewhere in between these two forces, and we want to find this direction, theta. And theta is given by tan inverse of y component over x component. So theta is tan inverse y force, or y direction force, is vertical force 550 Newton, and x direction force is 188.4. So let's find what that is. So tan inverse of 550 over 188.4, so that gives me 71.09 degrees, or theta is equal to, just say, 71 degrees. Now let's look at worksheet 17. So the first problem is finding the net torque due to the forces. Okay, so let's find the individual torques due to these forces, and then we'll add the torques to get the total torque. So let's call this one force F1, this one force F2, and this one force F3. So we want to find total torque, which is torque due to force F1, torque due to force F2, torque due to force F3. So for the force F1, force is applied at the on the circumference, and the distance between the center to the circumference, this distance is this big radius, which is B, okay, and then force is F1, and sine of angle between this distance and the force, which is 90 degrees. And when you pull this wheel in this direction, it tends to produce clockwise rotation, so its torque is negative. For T2, or for force 2, so when you pull this wheel to this direction, it tends to produce counterclockwise rotation. Okay, if you pull this way, then it will be rotating counterclockwise. So this sign would be positive. Distance between the point where you apply the force and the pivot, in this case the pivot is the center, so this distance is small radius, which is A. Force here is F2, which is 12 Newton. We'll use that in the next step. And the angle between force and this distance is 90 degrees again, so sine 90 degrees. And then this force, if you apply this force this way, then it will rotate this wheel in clockwise direction, so that means the torque would be negative, and the point where you apply the force and the pivot is B distance apart. Okay, so that's the distance between these 2 points, B. Force here is F3, and then sine angle between this distance and the force is again 90 degrees. Okay, so now plug in the numbers. We have B of 25 centimeters. In terms of meters, it would be 0.25 meters. Force 1 is 10 Newton. Sine 90 is 1. A is 10 centimeters, which is 0.1 meter. F2 is 12 Newton. And B is 0.25 meters. F3 is 9 Newton. Okay, so do the calculation. That will give you the net torque. Okay, so let's see what you get. So negative negative 0.25 times 10 plus 0.1 times 12 minus 0.25 times 9, that is negative 3.55, and the unit for torque is Newton meter. That's the total torque. Okay, so this negative sign implies that the net torque will rotate this wheel in clockwise direction. Okay, so by applying these three forces, the wheel would rotate in clockwise direction. So that's number one. Let's look at number two. Number two looks a bit complicated, but it is not that complicated. Okay, if you use the simplistic model, then you can easily solve this problem using the conditions for static equilibrium. So we have a 50 Newton bowling ball held by the person's hand with the forearm horizontal as shown in the figure. So this biceps muscle is attached to this point, which is 0.03 meters from the joint. So this is the joint, and the ball is 0.350 meters from the joint. So here we want to find the upward force F exerted by the biceps on the forearm. Okay, so we will consider that this bicep muscle is more or less vertical. Okay, although there is a little bit of angle here, but we'll consider the ideal situation here and consider this to be vertical like that. So this force is F, and that's what we want to find. And also there is force of this humerus bone on the joint. Okay, so there is a downward force due to this bone, which we call R. So we want to find F and R. So we can again model this by a simple extended free body diagram. So consider this to be the forearm. So we have weight of the ball vertically down, call that WB. There is force of this biceps muscle upward. Okay, so that's F, and there is this pivot. We are considering this to be pivot. The joint is the pivot, and there is force of the humerus bone on that pivot pointing down. So let's say that's R. Okay, and this distance is given, and also this distance is given. Okay, so here this system, which is your arm, is in static equilibrium. Okay, so apply, this is number 2, apply the conditions for static equilibrium. So there's no force in x direction, so we don't need to worry about this condition, although I can write right here, but this is not relevant. The second condition is Fy is 0. The third condition is sum of torques is 0. So let's apply this the second one, sum of all the forces in y direction. So consider up to be positive y and down to be negative y. So F is positive, R is negative, and WB is also negative. that is equal to 0. That's the second condition. Third condition is torque due to each of these forces is 0. So torque due to R would be 0 because this R is 0 distance from the pivot. Okay. In other words, torque is RF sine theta. So for R, R is 0, force is R sine sine 0 degrees. And then for this force, if this is pivot, then this force tends to rotate this counterclockwise. So plus distance between this pivot and this force, this distance is 0.030 meter, and the force is F. And then this weight is pointing down, so it tends to produce clockwise rotation if this is the pivot. So that will be negative. Distance between the weight and the pivot is 0.350 meters. And here force is the weight of the ball, that is equal to 0. Okay, so we have two unknowns here, so we don't want to use this one first. So let's first use this one because there is only one unknown in this case. Weight is known, this is 0, so this is the only unknown quantity. So 0 plus 0.030 meter F. So take this thing to the right side, it becomes negative, becomes positive. 0.350 meters times WB, and W is mg, mass times acceleration due to gravity, or we don't even need to do that because the weight is given. So if it were mass, then we would have to use mg, but since it's weight, so we can just plug in the number here. So then F, to find F, divide both sides by this number. So F would be 0.350 over 0.030, and WB is 50 Newton. So do the calculation and see what you get. So that gives me 583 Newton. So once you know this, now you can use this equation. So F is 583 Newton minus R minus 50 is equal to 0. So 583 minus 50 is 533 minus R is equal to 0, and then R would be 533 Newton. Okay, that's how you do that. Now let's look at number 3. So in order to do number 3, so we first need to discuss a little bit about stability of an object. Okay, so let's talk about what condition we need to satisfy for the stability of an object. So let's consider an object, this yellow object, rectangular object, which is standing on the surface. Okay, so the weight of this object is concentrated at this point, which we call center of gravity. So that's x is the center of gravity, and center of gravity is h distance from the base. Okay, this is the base of support. The part that is touching the surface is what we call base of support, and center of gravity is h distance from the base of support. And if the weight is concentrated at the center of gravity, then the weight would be pointing from that point down. Okay, and in this case, this height, which is this dashed line, and the weight are on the same line. Okay, so if we consider the angle between h and w to be theta, then in this case this angle would be 0, okay, because they are on the same line. So this condition where the center of gravity is exactly above this middle point of the base of support, or where the angle between h and w is 0, is called stable equilibrium condition. Okay, stable equilibrium means it's the condition in which the object remains at rest unless you disturb the object. Okay, as long as there is no external disturbance, the object will remain at rest, and even with a small disturbance it will come back to its original state. So that's the stable equilibrium. If you slightly move the object, it will again come back to this state. So it's stable equilibrium. Now let's tilt this object slightly to the right, and when you tilt that, you see this height of the center of gravity from the base, this base of support, and this w, weight is again vertically down. These two form angle theta. Okay, now again there is angle theta between h and w, and this weight, which is vertically down, is still within or still inside this base of support. This is the base of support. You see, this is still inside the base of support. It's not outside the base of support. So up to this distance is base of support, and this is outside the base of support. So as long as the weight is within the base of support, if you let go of this object, it will go back to this stable equilibrium. Okay, if you tilt it further more, you will get this condition where this weight, which is again vertically down, will fall on the pivot. Okay, this is the pivot because this object is rotating about that point, and up to this point, if you let go of this object, it can still go back to this stable equilibrium condition. Okay, so this is the critical condition. Okay, and if you tilt it further more, now it won't go back to the original state. It will just topple. Okay, it will become unstable. So this condition is still equilibrium, but just with a little bit of disturbance, this can go into unstable condition. So this is called unstable equilibrium. Again, this is still equilibrium, but it's unstable. Unstable because with a little bit of disturbance, it can topple, or it can go into unstable condition. Okay. So in this condition, the angle formed by h, this height, and w, weight, is called the critical angle. Okay, and this angle is given by this equation. How do we get this? So if we look at this triangle, this is right angle triangle. I don't know why it's doing this line. So whenever I draw something on the PowerPoint, it gives me some this random lines. Okay, so just neglect that line. So this angle is 90 degrees. Just we are considering this triangle, right triangle. So if I take tan this angle theta, that is tan is opposite over adjacent. Here opposite of this angle is half of this base of support. Base of support is t, the width of the object is t, and it's half of that. And then adjacent is this line, which is h. Okay, so then tan, theta c, or critical angle, would be tan inverse of t over 2 over h. Okay, so that's the critical angle, which is what we have here. Okay, or I can also write this as tan inverse of this. Take this 2 to the bottom denominator, so t over 2h. Okay. So up to this angle, you can still go back to the stable equilibrium. So this is the critical angle. If the angle is even slightly greater than that, then you have unstable condition. Okay. So here you see the angle now is greater than the critical angle. Up to here it's critical angle, but now this angle is greater than that critical angle. Now again also we see that the base of the weight, this red line or red arrow, is outside this base of support. Okay. So two things to be considered here. First thing is the angle between h and w is greater than the critical angle, and this weight is outside the base of support. So in this condition, the object topples, or it becomes unstable, which is also called non-equilibrium. Okay. So if you are asked what's the condition for an object to topple, the condition would be either the weight needs to be outside the base of support, or the angle is greater than the critical angle. So how do we make an object more stable? So in order to make an object more stable, we need to increase this critical angle. Greater the critical angle, more stable the object is. Okay. So like here, if we see a car in this normal condition, so you see the car's weight is within the base of support or inside the base of support. Now you tilt the car a little bit. For some reason the car tilts. The weight is still inside the base of support, so it can still go back to this stable state. Now in this condition, if the tilt is increased, then at some point this weight will be exactly over this pivot. So this is the critical condition. Okay, up to this point the car can still go back to the stable state, and the angle corresponding to that is critical angle. Now if you tilt it further, you see this is the base of support, and this weight is now outside the base of support. So the car won't go back to the stable state now. It will just roll over. Okay, or now it's unstable. So again, our aim is to increase the stability of an object, or in this case a car. So to make it more stable, or to improve the stability, we want to increase the critical angle. So there are two ways to increase the critical angle. Okay, one is by increasing the T, or the base of support, by making it wider, or by decreasing this one. Okay, so to increase theta, we need to either increase T, this numerator, or decrease H. Okay. We are, I think, out of time for this lecture. We will continue this in the next lecture. We will talk more about this next time.